So we now know that our physically realizable filters we must have the time domain transfer function equal to 0 before time equals 0. And this criteria is saying that we need to have these causal systems. So you can't have a transfer function that reacts to an input that has not happened yet. It's simply impossible to realize in the physical world. We also have this other mathematical definition which says that if you have the transfer function, its amplitude response, it can't be equal to 0 for any finite band. So if we need to make real filters, so we want to make real filters that approximate or get close to the same things that we wanted out of the ideal filter, then we're going to have to get a little creative because, right, our ideal filters, they have a constant amplitude response and they have a constant slope in the phase response. And so we need to figure out some way that we can get close to that ideal filter while still satisfying these true criteria. And we've just learned, right, that it's difficult to satisfy those criteria because our ideal filters have that brick looking frequency response. And this rectangle function is going to translate into a sinc function in the time domain. And what we've just learned in these past videos is that this is going to make it very hard to actually realize these ideal filters in real life, because you can't take something that has this exact frequency response and actually build it. So what is the alternative? Let's think about some alternatives that are possible. The first, or one of the main ways, is, right, we could take our sinc response and we could start working backwards. So let's say that we have a sinc response to the system, and ideally the sinc response would start before time equals 0, but we're saying, okay, we know this is real life and we can't have this. So let's start with the time domain function, and we know, okay, we could now if we could somehow realize a time domain transfer function that looks like the ideal transfer function multiplied by this step function, now we could make this into a causal system. So let's think about this some more. And going back to this picture, what we should remember from that previous video is that if we increase this time delay, right, so this is time delay 1 of 1 millisecond. If we increase it to time delay 2 of 2 milliseconds, we can see that this really big part of the sinc response goes further and further away from 0, and that in the time before 0, the amplitude of this is going down, so it's contributing less and less. And you can see that as you get even bigger and bigger time delays, that you're going to just continue to reduce the amplitude that your ideal time domain transfer function has before time equals 0. So keeping this in mind, we can see that one way, right, you could have, if you kept increasing your time delay larger and larger, it's going to have less and less effect before 0. So the response before time equals 0 is going to be less important. This is to the point where you could say, well, you could build a practical filter if you had an infinite time delay. In real terms, right, that means like you could add a slightly longer time delay, and you might be able to force that HT-UT into a position where now your approximate transfer function, you're able to cut this off here. And for the yellow one, you can see that this is getting smaller, and this h of t is going to become closer and closer, right, to approximating your actual ideal transfer function, which is what would be good. Another way that this is commonly done is using filters such as the Butterworth filter, which can approximate these cutoffs by adding higher orders of filter. So by creating filters that have this type of approximation, we can see that you never quite get that perfectly steep response results in that sinc function. So there are some tricks like Butterworth filters that allow you to get close to approximating ideal filters while still maintaining realizable characteristics. The drawback to this, and this is a bit beyond the scope of this book, is that as you get close to the bandwidth of interest, the phase response on this is going to be pretty unusual and is going to be add quite a bit of time delay. So even whenever you're trying to realize a filter, you're going to have to make some kind of trade-off.